B of STOC 2020 is a session on quantum computing, and the talks, each talk will be a 5-minute talk followed by 5 minutes of Q&A. I'm not going to be able to flash timer, so I'm counting on the speakers to monitor their own time and stop after 5 minutes. And yes, so the first talk will be by Mehdi Solimanifar. Is that okay? I see. Well, at least we keep the tradition of the session chair butchering the speakers' names. So at least some things didn't change in the virtual format. And Mehdi will be talking about classical algorithms, correlation decay, and complex zeros of partition functions of quantum many-body systems. And let's hear from Mehdi.
All right, thanks. So yeah, I'll talk about a joint work with Aram Harrow and Saeed Mehraban, which is about quantum spin systems. So the motivation comes from physics, where physicists would like to understand the properties of a system that consists of interacting quantum particles that we call a spin. So the interaction between these spins is described by a local Hamiltonian, which is basically the quantum analog of a constraint satisfaction problem. So in general, the local Hamiltonian is an exponentially large matrix in terms of the number of spins, but it also has a structure. It's sum of local operators. So a quantity that physicists and people in quantum computing would like to evaluate about the system is the partition function, which at a given inverse temperature beta is defined to be the trace of e to the minus beta times the Hamiltonian. So since the Hamiltonian is large, exactly evaluating this quantity is hard. What we want is approximation algorithms. So the classical version of this question is well studied. We know that the hardness of approximation depends on the inverse temperature. And in particular, there is a critical value below which there are efficient algorithms. And above that, it's NP hard in the worst case to estimate the partition function. So this transition in the hardness is related to a physical phenomenon called the thermal phase transition. There are at least two ways to characterize the efficient phase. One is based on the decay of correlations between the spins, and one is based on the complex zeros of the partition function. So this is all about classical spin systems. The same picture in the quantum settings is not yet fully established. In our work, we consider this question, and we make progress on that by lifting some of the classical results due to Dobroshin and Schlossman and Barbinok to the quantum setting. So our first result is a quasi-polynomial time algorithm for approximating the partition function that works in the zero-free region, which is basically that efficient phase in the previous slide. And the proof idea is the following. So beta is the inverse temperature, is the real parameter, but let's consider it to be a complex one. And let's consider the partition function on the complex beta plane. And let's look at the zeros or the roots of this function. So it turns out that there is a region which is free of these zeros. It includes the real axis. It includes beta equals 0, meaning infinite temperature. And it extends to some critical value where the zeros get very close to the real axis and block the way. So inside this zero-free region, the log of the partition function is an analytic function. And powerful things like analytic continuation or Taylor expansion of work, they converge in this region. So in particular, it turns out we can estimate the coefficients of the Taylor expansion of the log at beta equals 0 in quasi-polynomial time. So this allows you to extrapolate and find the value of the partition function at some non-zero constant beta. So this is the algorithm, but how do we actually find the zero-free region? How do we locate the zeros? So in our second result, we show that at least there is a disk of constant radius where the radius is proportional to the 1 over the degree of the interaction graph, and it depends on the other parameters in the Hamiltonian, such that there are no zeros inside this disk. So the proof idea is this. We consider a subset of the spins and the partition function of that subset. And then we ask what happens if we add one spin to the subset. how much the partition function shrinks. So we give a lower bound on the value of the new partition function. And if you iterate over this, it gives you a non-zero lower bound on the value of the overall partition function. And the proof idea is by using cluster expansions, which is a way to basically single out the effect of adding one spin to this like complicated partition function. So if you recall, I said there are two ways to characterize the efficient phase. One is based on the decay of correlations, and one is based on the complex zeros. In our third result, we make a connection between these two. And we show that at a given real beta, if there are no complex zeros around it, at that real beta, the correlations between the spins decay exponentially. And we show that if the spins that we are measuring the correlations are at least logarithmically far away, or if the Hamiltonian has a structure, it's either commuting or it's on a one-dimensional chain. So the way we do this is by defining a specific function that measures the correlation between the spins, and it has a specific properties. So one is that if the partition function is not zero, this function is analytic. And also its low order derivatives at beta equals 0 are 0. So it looks very flat near the origin. And since it's analytic, if you move to a constant beta, it doesn't blow off or anything. The value remains close to what it was near the origin, which is a small amount. Therefore, the correlations between the spins are also small, and indeed they're exponentially small. So we also have algorithms for a specific family of Hamiltonians called ferromagnetic. This works for any inverse temperature. It doesn't stop at a critical value. And the idea is to, instead of Taylor expanding with respect to beta, we Taylor expand with respect to another parameter in the Hamiltonian. And we need to locate the zeros with respect to this new parameter, which can be achieved. And this also gives you a quasi-polynomial time algorithm. All right, so I stop here and see if there are any questions. Thank you.
Thank you. Thank you, Mehdi. And maybe one attendee asked if you can explain a little bit the significance of the result. What are the applications?
Right. So, yeah, as I said, in physics, we would like to evaluate the partition function, because if you have that, then you can read many other quantities that you would like. So the partition function is something that encodes many other useful information about the system. So, you know, like at zero temperature, it's a well-studied question to estimate the energy of the system. At finite temperature, the right quantity turns out to be this partition function. It's like a very useful thing to have. In quantum computing, it also has applications, because in many algorithms, people prepare the Gibbs state, which is the state of these spins at a fixed temperature. And by sampling from that, they can basically solve like optimization problems similar to like simulated annealing and things like that. Okay. So as a part of that, you need to estimate the partition function.
And another question, they ask if this phase transition happens in the sampling of the Gibbs state, and if so, is it the same transition point as the computational transition?
So in the worst case, from the classical side, we know that there is like a specific Hamiltonian where this matches the physical phase transition matches the computational one, and this carries over to the quantum case. But we don't focus on like a specific family of quantum Hamiltonians that we can like pinpoint the physical and the computational one to be the same.
But do you conjecture that these things are the same?
I mean, yeah, in the like quantum Hamiltonians include classical Hamiltonians, and we know for those that in the worst case, they match. But this doesn't mean that for any system, there is such transition. You know, like it could be that you can pass the physical phase transition without like encountering the computational one.
Right, and I guess there are two questions that people are asking, which maybe you can answer them both as one, because we have a minute. is basically about getting quantum. So can you use the result to get a quantum algorithm for sampling quantum Gibbs state? And another version is what's the meaningful sampling version of the problem? And maybe you can answer both at once.
Yeah, so there are like ways to sample from the Gibbs state by using the partition function. So if you have an oracle that gives you the value of the partition function, then you can sample from the Gibbs state. This is like the equivalence between counting and sampling. This is not, again, like fully established in the quantum settings, but certain sampling algorithms for the quantum partition function can be obtained just by giving an approximation algorithm to the partition function the way we do.
Okay, so let's, there is one last question, but maybe I'll let you answer that by text so we can move on to the next speaker. So yes, thank you, Mehdi, and the next speaker will be Ewan Tang, and yes, you can unmute yourself. That's very good. So yes, Ewan will be talking about sampling-based sublinear low-rank matrix arithmetic framework for dequantizing quantum machine learning. And Ewan will, you have 5 minutes, and then we'll have the Q&A.
Okay, sounds good. Can you hear me? Okay.
Yes.
Okay, cool. So I'm going to be talking about this paper. I have 5 minutes, so that's basically just enough to talk about the motivation. And okay, so this paper is about exponential speedups in quantum machine learning. So at first glance, a lot of quantum machine learning algorithms seem to admit exponential speedups for useful tasks. This is because they run in time polylogarithmic in input dimension, whereas classical algorithms typically solve the analogous problems in linear polynomial time. However, these exponential speedups are a little bit odd because they might not manifest in practice. Unlike their classical counterparts, these QML algorithms have to make strong input assumptions and learn relatively little from their output. This is an observation, for example, made by Scott Aronson in Read the Fine Print. So basically what this means is that these algorithms are, sublinear algorithms. And so the input model they assume, which is often something called QRAM or analogs of this, need to have some stronger input model to allow you to do anything. And on this slide, I've basically color-coded kind of subjectively what applications, how close each proposal is to solving these issues. And when I do this color coding, these are all not as good as, for example, Shor's algorithm, which achieves an exponential speedup while using the same input and output as classical factoring algorithms. Now, these speedups have recently started to better understand them. So in last year's STOC, I showed that this quantum recommendation systems algorithm on the bottom right by Karenides and Prakash does not give an exponential speedup. And I did this by describing a classical algorithm that performed the same task up to polynomial slowdown. And there's been a lot of subsequent work using similar techniques to dequantize a whole range of quantum machine learning algorithms. And what this shows is that the advertised exponential speedups of these algorithms sort of disappear if your corresponding classical algorithms can use input assumptions that are as strong as those of the quantum algorithms. And so as a consequence, these dequantization results have been really a significant altering of our landscape of QML speedups. Now there's another line of work that basically unifies all known quantum linear algebra algorithms under a framework called quantum singular value transformation. This is work done by, for example, Gillian et al. Also in STOC, I think last year. And since this framework is BQP complete, so for example, it contains this sparse linear systems problem, which is BQP complete. We cannot dequantize it in full. However, if we restrict this framework to the QRAM-based input model, these examples of BQP completeness don't occur. And this suggests that it might be possible to generalize these techniques to all of QRAM-based QSVT. And of course, the natural question here is whether we can do this. Okay, so now our results is that we do give such a framework. I won't explain like why we consider this to be an analog, but basically this framework captures the same capabilities of QRAM-based QSVT up to sort of approximation error and polynomial slowdown. And this gives strong evidence that quantum linear algebra based on QRAM admits no exponential speedups. This is because we believe that QSVT basically captures all of our known techniques for quantum linear algebra. And we show how to use this framework to recover results on, we give a classical analog to sort of like a weaker model of quantum singular value transformation. We show a bunch of other results on generic forms of matrix functions. And we also recover a lot of prior work on dequantizing quantum machine learning. And we give some new applications. So for these latter 2 points, here's a chart showing the applications that we looked at. And we recover all of these with at least as well as the prior work does. And I just put check marks here indicating when it's indeed even faster or even more general. And we also give additional results for low rank Hamiltonian simulation. And this discriminant analysis algorithm, this quantum machine learning algorithm by Tsong and Duan, we dequantize it. Okay, I'm done, thanks.
Thank you, thank you. So yes, people can ask questions on. You can either ask questions on the Q&A, or you can also raise your hand. Raise your hand virtually. Yes. So yes, first question is there a mildly realistic example where we can actually use or we can actually assure these kind of strong classical input assumptions?
Yeah, so you can get these input assumptions by paying input sparsity time, so n and z of your input. And this means that if you look at like standard sketching algorithms, this is sort of like a restricted form because they're allowed to pay n and z of a, but they're allowed to do anything with it, whereas we're allowed to pay n and z of a to make this data structure, and then we just have to spend time. That's polylog in dimension.
Okay, another question is, so the dependency on epsilon seems to be polylog 1 over epsilon using quantum SVD, but it seems like when you dequantize it, the dependency is poly 1 over epsilon. So does it mean there is still some kind of a speed up?
Yeah, this is actually a subtle question. The argument that we give is basically the following: the epsilon differences, you have for quantum machine learning algorithms, you have to pay them eventually, in the sense of like, even if I get my output state with log 1 over epsilon dependence, if I want to use this quantum state in order to measure anything or like estimate any value, I have to pay 1 over epsilon eventually. So basically our classical algorithms have to do that because it's like, we see all the values we see all the entries of the output vector. And so this is why we have to pay 1 over epsilon. I'm not confident, I'm not sure, I couldn't really figure out how to exploit this 1 over epsilon versus log 1 over epsilon thing, generally.
And there is another question. Does it mean that we have to change all QML, I'm assuming this is quantum machine learning models based on QRM, that's maybe QRAM or?
Yeah, so I don't know. So you could try to change your model. Like you could try to change what QRAM is. That's how I'm interpreting this answer. But there's not a lot of easy ways to change QRAM to make, like I couldn't, it's like somehow these algorithms are sort of resilient or robust to changing your input model in sort of these minor ways. Like it's probably more, yeah, I don't know.
So, Yes, and one more question. Do you have any thoughts whether one can expect classical analogs for sparsity-based quantum machine learning speedups?
So actually, I don't know to answer. I mean, like some of these problems are BQP complete, so maybe not. But actually, in fact, you can run these algorithms for all of the sparsity-based quantum machine learning. Like you can run a version of HHL. The issue is that the error just blows up because the error scales as Frobenius norm, whereas the algorithms scale is like something like spectral norm. And so, yeah, you like things get bad really fast, but you could theoretically run it. I mean, if you wanted, if you had something that was like sparse and low rank, I don't know, but yeah.
Okay, so yes, so is it fair to say that one way to view this result is that now the fine print has become bigger than the big print, or is it?
Yeah. I guess it's like the fine print. It's like the ad is like at the first, the like a small thing, and then there's like a mountain of fine print.
Okay, thank you very much. And the next speaker will be Dmitry Gavinsky, who will talk about, and let me unmute Dmitry.
Hello.
You are unmuted. Very good.
Just now.
Yes, and who will talk about bare quantum simultaneity versus classical interactivity in communication complexity.
All right. Let me share the screen.
Yes.
Hello. So can you see the screen now?
Yes, we can see it.
Okay.
We can see it well. So as usual, 5 minutes and 5 minutes for Q&A.
Sure. Okay. Hello. Thank you very much for your interest. And let me use this opportunity to make a short appendix to the main presentation to go briefly through the history of the separations between quantum and classical communication complexity. The reason I want to do it is that intuitively we are getting rather close to being able to answer most of the questions that we had in the beginning of this line of research, comparison between quantum and classical bipartite communication complexity. So I think it's very helpful for us to get some feeling of what is still important and what is missing for our understanding, to have a look at the historical background as a landscape. So let me go briefly through the results. Something similar I already did on the main talk, but here it will be slightly more detailed, I hope so. The first result in the list, which can be viewed as qualitative demonstration of qualitative advantage of quantum communication over classical, is from year 1998 by Berman, Cleave, and Wigderson. And there they gave a partial function that had an efficient quantum, but no classical communication protocol. And here the limitation of that result was that they only considered zero-error protocols. And you can probably agree and feel that, in the context of quantum communication, especially where everything is randomized, this limitation, it feels unnecessary and it feels artificial. So indeed, the next result, which we saw, is from 1999 by Raz. He demonstrated a partial function that had an efficient quantum two-way interactive protocol, but it had no efficient classical two-way protocol. You can see that both of the, and now this result, starting from this one and all the rest I'm going to mention now, they are results for bounded error, for the bounded error regime. So no longer we're facing this restriction of zero error. And you can see that in both these cases, the object, the problem that were analyzed are partial functions. It will be important for the rest of the results. The next result in the list is a total function. It was shown in 2001 by Berman, Cliff, Watrous, and de Wolf. And this is a very special, in many ways, a unique result in this list of separations. You can see that here the object, as I said, is a total function, which is the most restricted type of communication complexity problems. And they demonstrated separation between quantum SMP and classical SMP without shared randomness. So for the function which analyzed was the equality function. Equality function has an efficient protocol in classical SMP if you allow shared randomness. So lack of shared randomness was a crucial part. And this is the only separation fact that we've seen so far that uses total function, the most restricted type of communication complexity problem, as the object used to demonstrate the separation. The next result in the list is from year 2004. It's a separation due to Borisev, Jaram, and Kironidis, and they did the following. They demonstrated a relation. You can see a relation is a new type in this list of separating objects, of separating problems, and it is the most relaxed. So it gives us the definition allows us the largest amount of flexibility, which means using this type of problem for separating classes is the easiest. If we separate something via more restricted type of objects, we do harder, we perform a harder task, which means our result gives a stronger indication that one class is stronger than the other. So they separated via relation quantum one-way from classical one-way communication. Again, it's bounded error setting. And it was open whether same separation could be done via partial function, which was proved 3 years later in 2007, joint work with Kempe, Kironidis, Raz, and de Wolf. Exactly same separation, but the object was a partial function. Next result in the list is from year 2008. A relation was shown that had an efficient quantum one-way protocol, but no classical two-way protocol. You can see here that we are, so to say, entering a new type of separations, new terrain, if you wish, where the layout of communication complexity models that we are talking about, they are going in favor of classical. So even though here quantum is just one way and classical is two-way interactive, nevertheless, for some specific problem, a relational one again, it is possible to see that even more restricted version of quantum offers exponential advantage. 3 years later, 2011, Clark and Regev did the same separation via a partial function. Again, as before, this is strengthening because type object is more restricted. 5 years later, 2016, a partial function was demonstrated, separation by a partial function, where there was an efficient solution in the quantum SMP model with entanglement and no efficient solution in the classical two-way model. So here we can see that the gap between the layout, so to say, of quantum and classical models is even wider because SMP is weaker than one way. But the price that we pay for this, in some sense, stronger separation is the need for entanglement. In order for an efficient quantum protocol to exist for that partial function, entanglement was crucial and necessary. In 2018, a partial function was given. This is slightly different type of, actually it should be compared to this result I mentioned earlier from 2001, total function with efficient quantum SMP, but no efficient classical SMP. So there, as I said, it was crucial that the classical model did not allow shared randomness because equality has a simple protocol. Now, in this case, classical protocol SMP, even with shared randomness, still does not exist. It's still exponentially more expensive than quantum SMP without shared randomness, and the object being used is a partial function. Finally, the result, which we're looking at now, is a separation which, in terms of the model being separated, looks like the strongest we can hope for in the context of bipartite separations. quantum SMP, the weakest quantum, can be exponentially stronger than the classical two-way, the strongest classical. And the price that, so to say, the cost of this separation is that the object that we are using here is the most relaxed type of problems relation. So this is the history, and you can see here, I'm not going now to talk about open problems, but more or less everything that is not obvious from this line of results is open, because we nearly don't have any possibility results. So questions, what can be done via total functions, and whether, let's say, this separation, for instance, the most recent one, can be done via partial function is wide open.
Yes.
Thank you.
Thank you. Thank you.
Thank you. Any
So,
questions?
yes, are there questions? And yeah, as usual, the actual the talk, the full talk would be yeah, is on YouTube. So, any question? Yes. A question: do you expect the log squared n to be improved to log n in the quantum part?
You mean the most recent results, the one I'm talking about, right? I guess
Yes.
for the protocol we're looking, for the problem we're looking at, it's unlikely, because it could be that it's possible for some other problem, because it feels like the problem we look at, it really requires n trials, so to say, n, or let's say, or n to omega 1 polynomial number of trials. And in order to do that, we have to, you know, take down the error to 1 over poly of every single trial, which means intuitively it means that we need log square is needed there. But so I would expect that actually the best possible for this specific problem is something like log square, but maybe there are other problems that can do the same separation and have quantum protocol of complexity log.
Okay, any other question? Okay, so if there are no other questions, thank you, Dimitri.
Thank you very much. Thank you.
And the last talk of this session will be by Andris Ambainis. And Andris will talk about quadratic speedup for finding marked vertices by quantum walks. And Andris, if you can share your screen, and as usual, 5 minutes for the lecture, and then another 5 minutes for the Q&A.
So this is joint work with Andras Gillian, Martin Škokainis, and Stacy Jeffery. And the setting for this work is the following. We consider a class of algorithms that are based on search by random walk. That is, we have some search space, and we perform on a random walk on this search space. And we stop when we find an element of the search space with some property that we want. I'll be referring to such element as a marked vertex. So there is a graph, some vertices in it are marked, and the task is to find the marked vertex. There is a very well-known result that for every classical random walk search algorithm that satisfies certain constraints, there is a quadratically faster quantum algorithm. This was invented by Mario Szegedy and appeared in Fox 2004. And this has a number of applications. The first application was a quantum algorithm for the element distinctness problem, the problem of finding two equal elements in an array. And many other applications have followed, and this Szegedy's result has been among the most important tools for quantum algorithms. However, there is a little fine print for this Szegedy's result. And the fine print is that the quantum walk algorithm does not solve the same problem as the random walk algorithm. Namely, quantum walk algorithm solves the decision question. With this, it answers whether the search space contains any marked elements. It does not necessarily find them. So how is this possible? How could a quantum algorithm solve a decision problem without actually finding a marked element? The way this algorithm works is that one sets up a certain quantum process called quantum walk, which starts in a certain starting state. And if the search space contains no marked elements, the starting state remains unchanged. If there are marked elements, then this quantum walk gradually moves the starting state to a nearly orthogonal state. And then by measuring whether we are still in the starting state or we are somewhere else, we can check if a marked element exists. However, this nearly orthogonal state to which this quantum walk goes, it does not have to consist of marked elements. So with this quantum algorithm, we can answer whether a marked element exists, but we don't necessarily find it. And extending Szegedys result to finding marked elements has been a long-standing open problem in this area. For the case when the search space contains exactly one marked element, it was solved by Crowley et al. At ICAO 2010. So the result here is that there is a quadratic quantum speedup for the problem of finding marked elements. But for the case when the search space may contain multiple marked elements, this problem has been opened. And in this paper, we solve it. We construct a quantum algorithm for finding a marked element in time that is of order almost square root of t, where t is the classical time to reach a marked element. So almost square root of t means square root of t times polylog t. So thanks. I'd be happy to answer questions.
Thank you. Thank you. You even finished before time, which is excellent. So any questions? So let me ask a question if no one is asking. Is there, is this polylog term, does it depend on the number of vertices or just on the t?
Just on the t.
Just on the t, because if it's number of vertices, you could probably do some kind of a binary search or something, no? Or
yes, as far as I remember, there's no dependence on the number of vertices here.
Mm-hmm. Yeah. Okay, now, yes, Scott is asking, why couldn't you go from t to square root t by just reducing to the single marked item using Valiant Vazirani? So just hashing type of thing.
The issue here is that if we reduce to single marked vertex, we get square root of the time for the case when there is a single marked vertex. But in this case, with our algorithm, we get square root of the time for the actual number of marked vertices. So t, in general, depends on how many marked vertices you have. And if there are more marked vertices, then the time to reach one of them gets less and less. And if you do Valiant Vazirani, then you go back to square root of t for the case with single marked vertex when t is largest. So our goal was to construct an algorithm which achieves a quadratic instance speed up on every instance with respect to classical time for that instance.
Mm-hmm. Okay, yes. And so basically what you're saying is that the okay, so I think we got it. So another question. So there are two questions. One is the importance of finding what's the applications to find the marked vertex, and the other is to comment about the technique.
So I guess the importance is that for most of applications, we actually want to find the marked vertex. So if we are searching for equal elements in an array, we typically want to find them rather than just solve the decision problem. And in terms of techniques, I have another slide with a brief description of techniques. So basically, there are three technical components. So first component is there is this Segedis transformation from random walks to quantum walks. And we use the same transformation as Segedi. Then the second component is there is this modified walk called interpolated walk, which means that we modify the original walk so that whenever it is at the marked vertex, we stay there with a large probability, 1 minus epsilon, and we continue with probability epsilon.
And there is a question. Sorry.
And then, okay, so there is this interpolated walk. And then there is a third technique, which is a recent tool called quantum fast forwarding, which says that, which provides a quadratic speed up over random walks in a certain weird sense. We can apply a discriminant matrix of a random walk to a quantum state t times in quantum time order square root of t. So what we do is we start with this interpolated walk, and then we apply quantum fast forwarding to it. And the challenge is that, the technical challenge is that discriminant matrix may in general decrease the norm of quantum state. So this results in quantum algorithm which may succeed with very small probability. So what we have to do to show is that for this actual application of quantum fast forwarding, the success probability is actually large, and this state that we get by applying discriminant matrix is concentrated on marked elements of search space.
And the last question is, do you, if you were to know the number of marked vertices, does it help you shave some log factors or speed up in any way?
I guess not very much. Well, first of all, the number of marked vertices is not the key parameter here. The distribution of marked vertices also matters. The classical hitting time may change dramatically depending on whether the marked vertices are all in the same part of search space or they are distributed. So the right parameter to note would be the classical hitting time.
I see.
And so what happens? I think it's not very helpful. I think it's not very helpful. It might.
Yes.
Maybe it would shave some factor, but it would not shave off all log factors.
Okay, thank you. So yes, that was the last talk of this session. And enjoy the break, such as it is. And just a reminder that there is a senior junior lunch for people that signed up for that at noon Eastern time, wherever that your time zone. So thanks everyone for coming. Thanks the speakers. And yes, see you in future sessions. Thank you.